This is part 2 of the NP hard and NP complete problem. In part 1, we have seen what is a hard problem, what is a non-deterministic polynomial problem, and also we have figured out how to write non-deterministic polynomial algorithm for a given complex problem. And in this video, we will see how to convert a NP hard problem into NP complete problem. First of all, let us understand that there are numerous problem with exponential time complexity. But however, solving each of the problem individually is difficult. That is why in research, they select certain problems from the problem space and they solve the problem. If a new problem arrives, then the new problem is converted into the known complex problem. We can find some similarity between these two problems, then we consider that L and the known problem is identical. Now, if I can solve the known problem, or if I have a solution of the known problem, then it is considered that the same technique can be used to solve the new problem L. So this is basic idea of converting NP hard problem into NP complete problem. In this video is in continuation of the part 1, and in this video we will discuss how a complex problem can be converted into NP hard as well as NP complete problem. As it is said that if we get a new problem L, then we try to compare with any of the existing complex problem, and that problem is called benchmark problem. If we can transform L into the benchmark problem, then L is considered as identical to the benchmark problem. And if N can be, the benchmark problem can be solved, then L can also be solved. Benchmark problem used in this research is called the satisfiability problem. Satisfiability problem. This problem states that for any given Boolean variables x1, x2, and x3, we construct one CNF conjunctive normal form equation as x1 or x2 bar or x3 and x1 bar or x2 or x3 bar. The problem is we need to find out all the combinations of x1, x2, and x3 in such a way that the truth value of this equation is always true. So this is the problem, and in order to solve the problem, let's say we will use the brute force method first. We'll put all the values of x1, x2, all the possible values of x1, x2, and x3, and possible values are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and till 1, 1, 1. Now this problem, to solve this problem, we have to examine each of these values, putting it in the given equation. We need total of 2 to the power 3 is equals to 8 combinations. If we have n number of elements, then it takes 2 to the power n time. Since it takes 2 to the power n time, this is definitely a exponential time algorithm, and this is considered in the same class of other complex problems. Now let us see the problem solution using backtracking approach. This is another method of solving the complex problems. Now let's say this is any arbitrary node, and what x1 can have a value of 1 and it can have a value of 0, either one of them. If x1 is taken as 1, then we will follow this path, and x2 can be 1 or 0. Similarly, x3 can be 1 and 0. So from starting from this point, we will have a solution in this line. This is similar to the last solution. Similarly, in this line here, in this point, the solution is 1, 1, 0, this point 1, 0, 1, this point 1, 0, 0, 0, 1, 0, 0, 1, and this is 0, 0, 0. So this is called the state. for the problem CNF or the satisfiability problem. So now we have the benchmark problem. We also have a solution, greedy approach solution, where it gives a time complexity order of n, order of 2 to the power n. And also we have seen the space tree for the problems satisfiability problem. Now our next phase is to compare any existing complex algorithm, and we will see is that problem can be converted into a satisfiability problem, or if satisfiability problem can be transformed to the problem that we have considered. For that, we are considering the 0 by 1 knapsack problem. We will try to transform the 0 by 1 knapsack problem into satisfiability problem. If we can do that, then we'll consider that satisfiability and the 0 by 1 knapsack problem is equivalent or identical. That's why if we have a solution for satisfiability problem, then we also have the same solution, or we also have the solution from the for the 0 by 1 knapsack problem. Now let's understand what is 0 by 1 knapsack problem. For a given set of items, let's say I1, I2, and I3, for example, we have given weights 6 kg, 7 kg, 3 kg, and also we have given profit 3, 4, and 9. And also we have a knapsack of maximum capacity of 12 kg, and we need to select the items in such a way that we can earn maximum profit by carrying in the given knapsack. But however, we cannot include all the items because the total weight of the item is 16. However, the capacity of the knapsack is only 12. So this is the problem. Now we will try to solve this problem, and later we will relate this problem with the satisfiability problem, and we will see whether both are identical or not. Let's solve the problem 0 by 1 knapsack problem first using the greedy approach. For that, we have items I1, I2, and I3, and the values of I1, I2, I3 can be either 0. 0 means item 1 is not selected, and 1 means item 1 is selected. So we can have 0, 0, 0 here. That means none of the items are selected. Obviously, it's not a valid solution. Or we can have 0, 0, 1, indicates that only item 3 is selected. 0, 1, 0, only 2 is selected. 0, 1, 1, 2 and 3 are selected. 1, 0, 0, only item 1 is selected, and finally we'll go till 1, 1, 1. So this is the solution using greedy approach for the 0 by 1 knapsack problem. And now let's consider the state space tree for the 0 by 1 knapsack problem. Let's take one arbitrary node, and in this line we'll write item 1 is selected, and this side item 1 is not selected. Similarly, in this side we will have item 2 is selected, this side item 2 is not selected. So this side item 3 is selected, item 3 is not selected, and this side also we will have the same structure. Here we will have right. So here it is item 3 is selected, item 3 is not selected, item 3 is selected, not selected, selected, and not selected. Here also item 2 is selected, here item 2 is not selected. So if we look at any one of the solution here, this solution has the value 110, then any other random point where we can see the solution, it is 0, 1, 0. This solution indicates that item 1 and 2 are selected, 3 is not selected. So we'll try to find out the profit. And here also item 2 is selected, 1 and 3 is not selected. we can also find the profit earned from this solution. This is the greedy solution for 0 by 1 knapsack problem, and this is the state space tree for the given problem. Now let's compare these two, the satisfiability problem and the 0 by 1 knapsack problem. Let us first place the satisfiability problem solution this side and 0 by 1 knapsack problem in this side. If we see the diagrams in both the sides, this diagram and this diagram, and if we remove labels on it, then it is difficult to figure out which diagram is for which problem. It implies that both the problems, the satisfiability and the 0 by 1 knapsack problem, is identical. Now, it is said that the satisfiability problem is transformed to the 0 by 1 knapsack problem using the reduction approach. Since now we have proved that satisfiability and 0 by 1 knapsack problem are identical, so if I can, or I have a solution, if I can solve the satisfiability problem, then 0 by 1 knapsack problem also can be solved in the same process. In reality, the satisfiability problem is a well-known NP hard problem. Also, we have transformed the satisfiability problem into 0 by 1 knapsack problem. That is why 0 by 1 knapsack problem is also a NP hard problem. So it implies that if I have a problem, instead of 0 by 1, let's say I have a problem L, which is a very new problem, we do not know any solution, we'll try to transform it to the satisfiability problem. But however, transforming from L to the satisfiability problem, it should take a polynomial time. If it takes, conversion takes, or transformation takes exponential time, then this is not considered as a valid process. And since L is converted into a satisfiability problem, that is why the new problem L is also known as the considered as NP-hard problem. Once we prove that an algorithm, a problem L is a NP-hard problem, then we will try to write one non-deterministic polynomial algorithm for the problem L. If I can successfully write one non-deterministic polynomial algorithm for L, then it will be considered as a NP complete problem. So to summarize, any new problem L, we try to transform it to a benchmark problem satisfiability. If we can do that, then the new problem is considered as a NP hard problem. Once it is proved as NP hard problem, if we can write one NP algorithm, non-deterministic polynomial algorithm, then problem L now becomes NP complete problem.